Hi, everyone. In this video, we're going to talk about solutions. So a solution is a homogeneous mixture of two or more substances. Basically, you can think about it as something dissolved in something else. And in order for something to dissolve, there has to be sufficient attraction between the solute and solvent molecules. And so the solute is whatever there is less of. So if we're dissolving salt in water, the solute is going to be the salt. And whatever there's more of, or what's doing the dissolving, is the solvent. So in this case, water is the solvent. So once again, whatever you're dissolving is the solute, and what it's being dissolved in is the solvent. So salt in water. Salt's the solute, water's the solvent. Now, solutes don't have to be solids. They can be liquids, gases, or solids. And they are evenly dispersed throughout the entire volume of the solution. You can't separate them by filtration, and you can't see the individual particles. They might make the solution colored, but you can't see the individual particles. And if you try and put it through a filter, they'll just go right through. So here's a chart just showing some typical types of solutes. So you can actually have gas in gas solutions. An example of this would be the air that we're breathing. The solute is oxygen. The solvent would be nitrogen. So the air that we breathe is actually like 2/3 or 3/4 nitrogen. Oxygen's only like 25% to 30% of the air that we're actually breathing. So because there's less oxygen, it's the solute. There's more nitrogen, so it's the solvent. You can have liquid solutions where you have a gas dissolved in liquid. An example of this would be like soda or beer. The gas is the carbon dioxide, and the solvent is water. You can have liquid solutions like vinegar. So vinegar is liquid acetic acid dissolved in water. Or you could have solids in liquids like salt water. Salt would be the solute, water would be the solvent. And less common, you can have solid solutions where you have a solid dissolved in another solid. The most typical example of this would be like a metal alloy, like brass. Brass is zinc dissolved in copper, or steel is carbon dissolved in iron. Typically, they melt the metals. And so when you're making the solution, they're liquid form, but then it cools. And so it's still technically a solution, even though it's in the solid form, because they are evenly mixed. Let's do a quick study check. Identify the solute in each of the following solutions. If you have 2 grams of sugar and 100 milliliters of water, well, the sugar, there's less of it, so that's going to be the solute. If you have 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol, well, because there's less of this, that's going to be the solute. 55 milliliters of water and 1.5 grams of sodium chloride. Well, definitely the sodium chloride is being dissolved in the water. And air, if you have 200 milliliters of oxygen and 800 milliliters of nitrogen, because there's less oxygen, that's going to be the solute. So once again, solute is whatever there's less of. So this picture is just showing how particles become evenly dispersed when they are dissolved. And so on the left here is a graduated cylinder full of water, and there's some solid copper sulfate sitting at the bottom. And if you let it sit for a long enough time, the copper sulfate will dissolve into the water, and it will become evenly spread throughout the entire volume of the liquid. And so initially the particles were all clumped together at the bottom, and then once they've dissolved, they're spread out evenly in the liquid. And so this is to illustrate that a solution has the solute particles evenly spread out through the entire volume. They don't just settle down to the bottom by gravity. They stay evenly spaced out in the solution. So the next couple slides, we're going to talk about types of solvents. And so on Earth, like 70% of the surface of our planet is water. So most of the solutions we're going to be talking about have water as the solvent. It's probably the most common solvent in nature. And water is a polar molecule. So recall that water has oxygen connected to two hydrogens, and there's two lone pairs on the oxygen. And because oxygen is more electronegative than hydrogen, you get a dipole where oxygen is pulling the electrons towards itself. And so each of these bonds is polar. And so the net dipole is going to be right up the middle. We would say that this is the partial negative end, and this is the partial positive end. So because of the polarity and the fact that there's an OH bond, water can hydrogen bond with other molecules that also have OH or NH. And so this will become important when we're looking at the interactions of water with certain solutes. Now, water is not the only solvent. There are other liquids that can be solvents, like oil or gasoline can dissolve things as well. But in order for a solution to form, you need the same type of intermolecular forces between the solute and the solvent. So a solution will form if you have a polar solute and a polar solvent. So if both things are polar, they're going to mix. Or if both things are nonpolar, they will mix. But if you have a polar solute and a nonpolar solvent, they're not going to mix. Or if you have a nonpolar solute and a polar solvent, they also won't mix. And so most textbooks use this term like, dissolves like. I don't really like that term, but what they're trying to say is that if you have the same type of intermolecular forces, things will mix. So if you both have hydrogen bonds, you'll mix. If you're both nonpolar, you'll mix. So let's take a look at a few examples of this. First one we're going to look at is solutions with ionic solutes. So in this example here, we're looking at sodium chloride, table salt. Sodium chloride is a solid where you have positively charged sodium ions and negatively charged chloride ions. And when you dissolve salt, those ions actually split apart from each other, and you have the sodium by itself and the chloride by itself. And the reason they're able to separate is because the water molecules stabilize them or hydrate them. And so if you look at the sodium ion here, I'm going to zoom this in so you can see it a little more closely. The sodium is positively charged. And so to stabilize that positive charge, the water will orient itself so that the partial negative of the oxygen is pointed towards the sodium. And so water molecules will form a hydration shell around the sodium and stabilize it through electronic interactions. Similarly, the chloride ion is negatively charged, and so the water molecules will surround the chloride with the partial positive side. So the hydrogen side of the water is facing chloride, and it will form hydration shells around it. And so as the salt's dissolving, these ions are pulling off one by one and being surrounded by water molecules, which stabilizes it and allows it to dissolve. And so the solubility of an ionic compound involves water stabilizing the individual ions. So that's solutions with ionic solutes. Now, small polar molecules can also dissolve in water. In this example, we're going to look at ethanol, which is CH3CH2OH. Because ethanol has an OH group, it's polar, and it can hydrogen bond with the OH groups of water. So if we zoom this in a little bit here, you can see that the ethanol molecule has an OH and water has an OH. And so these two polar groups are going to interact with each other and form a hydrogen bond. That hydrogen bond is because of the partial positive on this water molecule and the partial negative of this one. And so the partial negative lines up with the partial positive, and they are attracted to each other, and that allows them to mix. And so ethanol is the regular alcohol that people drink. And so this would be like what happens in, say, vodka or something. Vodka is not pure alcohol. It's like 40% alcohol in water. And the reason why alcohol and water mix is because of this hydrogen bonding. And so the alcohol molecules happily hydrogen bond and mix with water. So this is an example of a polar molecule as opposed to an ionic compound. Now, the last example we want to look at here are nonpolar solutes. And so a nonpolar molecule would be something like carbon tetrachloride, so CCl4. If you were to look at this molecule here, it's carbon connected to 4 chlorines. And because it's symmetrical, there is no net dipole. So this is a nonpolar molecule. And so it doesn't mix well with water, not at all. But if you have another nonpolar molecule like octane here, these two things will happily mix together because they're both nonpolar. And the attractive force holding them together is dispersion forces. That was one of the 3 intermolecular forces we learned about in chapter 6. And so if two things are nonpolar, they will mix together through dispersion forces. And so neither octane, which is gasoline, or carbon tetrachloride, neither of these mixes with water, but they'll mix together just fine. So let's do a quick study check. When solid lithium chloride is added to water, it dissolves because, now lithium chloride is ionic. And so when this dissolves in water, it splits apart into lithium plus and Cl minus. And so the lithium ions, because they're positively charged, are going to be attracted to the partial negative of the water. And the chloride ions, because they're negatively charged, will be attracted to the partial positive of the water. So remember, opposites attract. Right. So the lithium is going to be attracted to the oxygen of the water, and the chlorine is going to be attracted to the hydrogens of the water. Do one more study check. Which of the following solutes would you expect to dissolve in water and why? So sodium sulfate. Do we think this will dissolve in water? Well, it's ionic. And so when this dissolves in water, you'll get Na plus, and there's 2 of them. So you'll get 2 Na pluses and an SO4 2 minus. So because they're ionic, I would expect them to dissolve in water. So we'll give that a yes. Now, gasoline, which is nonpolar. Well, because it's nonpolar, that is not going to mix with water. Now, what about iodine? This one's a little tricky. This is an ionic, or excuse me, this is a molecular compound. It's covalently bonded. And so if we were to draw a Lewis structure of that, it would be iodine bonded to an iodine. And they each have 3 lone pairs. Now, this molecule is not polar because there's no difference in electronegativity, right? No one atom is more electronegative than the other, so there's no dipole, so this is nonpolar. And because it's nonpolar, I would not expect it to dissolve in water. Now, HCl. HCl is also a covalent compound, looks like this, but chlorine is much more electronegative than hydrogen, and so you get this strong dipole where the chlorine is partially negative, the hydrogen is partially positive. And so because this is polar, I would expect it to dissolve in water, which is also polar. Yes. And that's it for this intro. So I will see you in the next video. Thanks for watching.